All right, welcome back to Training Module 4.2, Supermini and Mini Application. This is part 3 of the application training for the Supermini and Mini systems, and this involves cutting conditions. So I'm your trainer, Edwin Tunney, Training and Technical Specialist for Horn USA Incorporated. Before we get too far along in the training, what you should understand about the Supermini and Mini systems really doesn't have to do so much with the system as it does with current machine spindle limitations. So oftentimes people don't really think about this in a holistic manner, but when you deal with small bores, so small bore components, it's very difficult to achieve the proper cutting speed that you're used to. For instance, 400 SFM is a very common cutting speed to use in steel, and but with small parts, it's very difficult to achieve that. For instance, if you have a 250 thousandths component, diameter component, then your RPM at 400 SFM is going to be 6,000 RPM. Um, it's difficult to achieve that. A lot of times, machines are not designed in the turning world, they're not designed to run those kind of RPMs day in, day out. So you might find that the 4,000 and 5,000 range is where you're running. So just keep in mind when you see parameters in the horn technical section, they're basing that on an 8,000 RPM spindle with a 20 thousandths diameter because we don't forget we do bores all the way down to sort of 8 thousandths and 8 thousandths of an inch, and so the RPM will really never be achieved on most conventional machines with respect to surface feet. You'll see what I'm talking about here in this chart, and this is true throughout the board for horn technical documentation. 46 surface feet to 361. So yes, that is a very broad range, but you're dealing with tools that range from sort of 8 thousandths all the way up to 6 millimeter or 236. So you're dealing in that low range of cutting speeds. So this is it's not a mistake, and it's not meant to be overly broad. It's just covering that situation where you might have an 8,000 RPM spindle and a 20 thousandths diameter part or inner diameter of the part. So you'll be right around 46 surface feet. The real way to handle this when you're dealing with any other size parts is to take the top end number and multiply it by 0.6 and use that as your starting point. You shouldn't have any problem with a tool failure in that range, and then go up from there. Most of the time, you're going to be especially if you're less than 1/4 of an inch diameter, you're going to be limited by the machine spindle. So however that machine spindle is run, if it's run at the max RPM or if it's back down, 500, 1,000 RPM. But this will keep you out of trouble across the different material groups. So with carbon steel, as an example, or alloyed steel, let's say high alloyed steel is well used, a 440C or an M2, you can run 295 surface feet is what we recommend as the book top end. You can then say, okay, 60% of that is 170 SFM. So just start there and then work your way up depending on how much productivity you need out of the part. Same thing for the K. So the irons, the heat resistant alloys, the iron based and cobalt based, the non-ferrous group, and the hard materials. So take your high end number, whether it be for a specific grade. So let's say with EG35 or EG55, you have 524 as the top end, take 50%, start there, and then work your way up. The other parameter to think about is the feed per rev. So the Supermini and Mini tools use feed per rev. So you'll notice that grooving, profiling, and face grooving more or less start on the same low end of 4/10 to 8/10 minimum, and that's important. Minimum feed is actually very important because if you run below the minimum, you're actually not running above the edge prep, so you're sort of rubbing the material rather than cutting. So you need to run at least the minimum for a given tool, and then the maximum 8/10 for grooving. Profiling is 2/1000, and face grooving is 2/1000. So 2/1000 per rev doesn't seem like a lot, but when you're running 4,000 RPM, you're going to be moving pretty quickly across the part. With the Mini, a little bit heavier, more aggressive feed, so 4/10 on the low end to 1 thou 2/10. Then in profiling, 1 thou 2/10 to 4/1000. Then in face grooving, 8/10 to 3/1000. So they're based on, always think the minimum edge prep. And this is true for horn cutting tools as well as any cutting tools. You can kind of get a guesstimate idea of what the edge prep is on the tool by what the minimum feed is specified at. It'll be just a little bit above that edge prep. Also, think about your depths when it comes to your cutting radius. So you use a larger radius for improved surface finish, but you also need to make sure that your depth of cut matches that. So in the case of a boring operation, you do have more than T-max. So if you're just straight boring into a part, you have more than T-max depth. You kind of have to figure that out, based on the tool. But you don't want to under, you don't want to use a depth of cut that's too low, because you can see once you wrap around the insert around this radius, the force kind of pushes your tool down into the part, thus giving you a more stable and consistent surface finish. So always keep that in mind. Try to run above the radius. If you're doing a roughing, more semi-finishing operation, try to go 1 times. If you're doing finishing, try to take at least half the radius. And then for the max, the roughing max, if you're doing profiling, is really the T-max value or the depth of groove value given. And then finishing, sort of take 25% of whatever the T-max is a good rule of thumb. Also think about, in this slide, think about the length of your tool. So what's the L2 value? How far is it sticking out from the fixation here to the holder? So with easy material, with steels, P group, N group, aluminums, and K, which is iron. So for an example, a 1018 low carbon steel, a 6061 aluminum, or gray iron, you can really go greater than 16 thousandths if you're in a short condition. And we're talking specifically about boring operations. If you're doing profiling, you cannot exceed the T-max because you're going to have a clearance issue. But for just straight boring, you can go greater than 16 thousandths. If it's long L2, so if you're extended out, you know, sort of 2 and 3 times here, make sure to stay within 8 to 16. The average material, so 4140s, 316 stainless or 420 stainless. If you're in a short condition, stubbed up L2, you can use 4 to 16. If you're long, use 8 to 16. Then difficult alloys like titanium 6Al4V, nickel alloys like 718 Inconel, or cobalt alloys like ASTM F75, just really difficult alloys. Sort of stay within 4 to 8 on the short extension, and also 4 to 8 on the long extension. Um, the diameter to length ratio, you don't get much benefit in stubbing up with the difficult alloys. They're just take your time with those to make sure you always have the best results. As with anything too, you know, we give these parameters as guidance, but you really can't see all possible combinations of machine conditions, coolants, material conditions. So take these as guidance, but you have to use also your own your own experience as well. If you look at the mini cutting parameters too, I didn't want to leave out the mini with respect to AP max. So understand that for the R geometry, for instance, you have an AP max and you also have a T max. So the AP max is more or less for boring, and the T max is more or less a profiling limitation. So always stay within on both values. But if you're boring, focus on AP max. If you're profiling, focus on T max. So you can see that ranges. T max is generally much less than your AP max, just because you have an angle on the back of the tool, and that limits it with respect to depth. So, for instance, on profiling, you're going to range anywhere from a half a millimeter or 19 thousandths. Then you can also find some that are even shallower, like 6 thousandths, 5 thousandths, 9 tenths. On the AP side, you can find, though, you can go up to 102 thousandths. So always check that, look at that, make sure, you know, look at the insert, um, and make sure you're not exceeding the chip former. When you're using the D geometry, it does do side turning, but it's not the primary function of this. So be sure not to bury this thing all the way up to the top here. It will have less effect of chip curling um, when it's past this dish up at the top here. But in side turning for inch, for instance, you can go 40 thousandths all the way up to 18 thousandths or 118 thousandths if you're on a 114 insert. So just keep all these depths in mind. With side turning too, just be aware that the D2 geometry can do side turning, but it's not the primary function of that. So always keep that in mind. All right, that's it for this part 3 of the horn training on application. Be sure to check back and subscribe to get all the latest horn videos from Horn USA Inc. on our YouTube channel. Thanks and have a great day.